So we're transitioning from proportions into means. So to kind of help you guys, just a quick little, saying to help you remember which one goes with which. You're going to have ZAP tax. So ZAP stands for Z star for proportions, right? So kind of like Z with the star is like the A, asterisk. Z star for proportions. Well, what does that mean tax must stand for? A T star for the X bars, which is the means. So that brings us to this question. What is a T star? We haven't talked about it yet because we've not ever talked about the distribution that is used specifically for means. So we are going to be using a T distribution for means. We do not use the standard normal Z distribution when we are doing mean problems. We use a T distribution. I have great news for you. It looks very similar and it works very similar to a Z distribution. Yes.
Does that mean there's a T value?
Yes, there is a T score. Yes, just like a Z score, there's a T score. Just like a Z star distribution or a Z star critical value, we're going to have a T star critical value. Everything works the same. It's just T's are going to be used for means. Z stars are used strictly for proportions. Okay, so why? The first question is why? Why are we using something different when we got so good at Z? We love Z. Z is a good friend of ours. We've been talking about Z for a long time, but why? Why somebody new? Okay, here's the deal. When we were talking about proportions, we only had to estimate one thing, a p hat, because that p hat was used in the mean and in the standard deviation formula. The p hat was the only estimated value we needed. When we're doing means, not only do we have to estimate mu with an x bar, that's one level of variation in our estimation, but we have to also estimate the standard deviation with an S sub x. So we have two levels of variability that is happening here. So I can't use my standard normal curve that is pretty nice and tight around that center. I need to use a different distribution that it accounts for the fact that we've got two levels of variability, x bar and S sub x. So because of the fact that we don't know sigma, we know we don't know the mean, right? We knew we didn't know p, we know we don't know mu, but we also don't know sigma. So that's a second level of unknown. So because of that fact, we're going to go to a T distribution that allows for a little bit more variability in our estimations. So because of the fact that sigma is unknown, we are going to use a T distribution. Because sigma is unknown, we're going to use a T distribution. So mu is obviously unknown. Sigma, we are going to use S sub x to estimate sigma. We're going to use S sub x to estimate sigma. So again, because we don't know sigma, we're going to estimate using the sample standard deviation. And because of that, we're going to use something called the T distribution. The T distribution, that's what we're going to use, T distribution. Really good news, you guys. It all works very similarly. It sounds very similar. There's just little bitty, tiny baby tweaks here and there. And most of which of those are going to be done in your calculator. Okay, so this T distribution. Real quick, let's talk about a couple of things about the T distribution. The T distribution is symmetric with a single peak at 0. Well, that kind of sounds exactly like the Z distribution. That's because it is. A Z distribution is symmetric with a single peak at 0. So here's the difference. A T distribution has more variability in the tails. There's more variability out in the tails. So that means that my estimations are going to be slightly more varied than they would be for a proportion problem, but that's okay because we know that we're estimating two things. So for a T distribution, which is on the top here, we have two levels of unknown. We have two unknowns, x bar and s sub x, that we're estimating. So we have two unknowns, x bar and s sub x, estimate mu and sigma. X bar and s sub x estimate mu and sigma. In a Z distribution, there's just one estimation, and it's x bar. So if I know sigma, I can use the Z distribution. But because of the fact that I don't know sigma, I have to use a T distribution because that's a second level of unknown. Got it? Yeah, I guess. All right, cool.
How would we decipher from a graph, like, let's say if we would write a statement about the graph, how would we?
I'm going to show you that on the next page, Raul. All right, so here's the good news. A T-score or a T-test statistic is a standardized value. And it tells us how far our sample is from the mean of the distribution in standardized units, just like Z did. Okay? So if we had a Z-score of 1.5, we knew that our sample was 1.5 standard units from the value that was claimed. If I get a T of 1.5, that means that my sample is 1.5 standard units away from what it was claimed. So it works all the same. Okay? Here's the kicker. There is a different T distribution for every possible sample size. How many different sample sizes can you take? Infinite. There is an infinite amount of T distributions, y'all. Where there's only one Z distribution, there's an infinite amount of T distributions. So they are specified by their degrees of freedom, which is abbreviated DF. DF, degrees of freedom. Let me try to explain to you guys what degrees of freedom is. Huh?
An American unit.
Yes. Degrees of freedom. Let's pretend there's 20 desks in a room. There are 20 kids in the hallway waiting to come in. When the first kid comes in, how many free options do they have on where to sit? If there's 20 desks in the room, 20 kids outside, first kid, how many options do they have?
20.
They got 20 options. They have a freedom to choose from 20 desks. They go sit down. The next kid comes in. How many free options do they have? 19. The third kid comes in. How many free options do they have? 18. Okay, I could do this all day, but I'm going to go ahead and hop down to the last kid. All these other kids are in the room. 19 kids are in the room in a desk. This last kid, how many free options do they have? Is it really a free option, though?
No.
They're stuck in that desk. So every other kid except the last one had some degree of freedom to choose where to sit. Now, yes, as the room filled up, their degree of freedom minimized. They had less and less choices. But everybody except that last kid had some degree of freedom of choice on where to be. Okay? So that explains to us how we find degree of freedom. To find a degree of freedom, we simply take 1 and subtract it from the sample size. So degree of freedom equals n minus 1. So for example, in this particular desk and student example, we had 20 students, n is 20. We subtract 1. That means 19 had some degree of freedom of choice. That's how you can think about it. There's a very long calculus proof that goes along with this. You don't care.
Yes, I do.
Do you? I can let you see it then. But it boils down to n minus 1 degrees of freedom because there are 19 free options. 1 is stuck in that last one. All right. Here's how you notate t with an n minus 1 degree of freedom. T with an n minus 1 degree of freedom would be it's a little t. If you make your little t's like a cross, which is fine, just be careful it doesn't look like a plus sign, okay? So here's an example like the one we were just using. It would be T19. T19. So that 19 is the degree of freedom. So what's the sample size if I'm on a T19 distribution? 20, okay? For example, T47. T47. What's the sample size in a T47 distribution? 48. Okay, that's how you can get the sample size if you know what distribution you're on. Just add 1. And vice versa, if you know the sample size, you can get the distribution. All right, when we're comparing, yes?
Could we use like a capital T because my T's are really like pluses?
Yeah. You can.
Is there like another notation that uses capital T or something?
I'm trying to think if there is. I don't think that there is. So, I mean, you can use a capital T. Yeah, that's fine. Yep. Okay. So, a couple of things here. Here's the picture that I was talking about. All right, the solid line that is closest to the x-axis and tallest in the middle, that is your z standard normal distribution. Okay, so there's our good friend, the z distribution. It's the one that's closest to the x-axis, tallest in the middle. The dotted line is a t distribution with 2 degrees of freedom. Now, if there's 2 degrees of freedom, what was the sample size? 3, okay? 3 was the sample size. There's 2 degrees of freedom. 3 minus 1 is 2. So there you go. All right. Notice that there's more area in the tail. There's more variability. Hello. There's more variability in the tail with this T2 distribution. Okay? That's because there's a lot of variability in my estimations when I'm only selecting 3 people out of the population. If I'm only getting 3 people out of the population, I might be getting 3 people that are kind of over here on this far side. That's one estimation, but I might get a lot of people over here on this side, or there's just a lot of variability that can happen because I'm not averaging out the weirdness as much when I'm only selecting 3 people. So I have more variability in the tails, less going on in the middle, okay? T9 degrees of freedom. What's the sample size? 10. So I'm increasing my sample size by just 7 people. And notice that my area in the tails is already decreasing by quite a bit. I'm already getting close to the standard normal curve pretty quickly. So it doesn't take long for your degrees of freedom and your sample size to get close to that standard normal curve. Good news. It will never surpass the standard normal curve. The t distribution will never pass the standard normal curve. Standard normal curve is like a boundary that it will not pass, okay? It will get so close that it will be hard to tell the difference. So you will see numbers and you're like, I thought that was the z-star critical value. Well, if your sample size is big enough, it's going to look like the same number. So you'll see that here in just a minute. So real quick, again, just a couple of little notes about this. A t distribution is approximately normal. Okay, it is approximately normal. It's single peaked. It's centered around 0. It's symmetric. It's normal. It's just not the standard z normal distribution. T distribution is more spread than z distribution. The t distribution has more area in its tails. The T distribution has more area in its tails. And as degrees of freedom increase, now let's think about that for just a second. How are the degrees of freedom going to increase?
Sample size increase.
The sample size is going to increase. Remember, degrees of freedom is just n minus 1. So the only way to increase my degrees of freedom is to increase my sample size. So as the degrees of freedom increase, the T distribution approaches the Z distribution, but never passes it. It's never going to go above it in the middle, and it's never going to get closer to the x-axis. It'll be so close sometimes that they're probably going to be like right on top of each other, but it's not ever going to pass it. So that's the T distribution. That's its attributes. Do you guys have any questions about a T distribution and what it kind of looks like and how it relates to a Z distribution? Why are we using a T distribution instead of the Z distribution that we know and love so much? Because we don't have sigma. We don't have the population standard deviation sigma. So we're having two levels of variability going on here. Okay? All right, so let's talk about critical values. So, does anybody remember, and I know this is way back in your memory banks, the Z star critical value for 95%?
Wait, is that the one where it's like each one, or is it just confident?
1.96. 1.96. You're thinking of the Z star critical value for 90%, which is 1.64. It's the one that goes 3 decimal places. 5. Okay? These were our Z star critical values from when we were doing confidence intervals and we were having to use Z star critical values. But do you guys remember how we figured those out? If we didn't know those, if we forgot what they were, do you remember how we got them? Yeah, so we made like a normal distribution and we said, okay, we want 95% in the middle. And so there's 2.5% over here. There's 2.5% over here. And so that means I have an area here of 0.025. And we shaded that in just for effect. It really didn't have to be shaded, but it was there. Whatever this boundary was and this boundary, they'd be the same number. One of them was negative, one of them was positive. And we went to our calculator and we found the Z star critical value by using what? Inverse norm. So if we went to inverse norm, we put in an area of 0.025. We put in a mean of 0 because we were on a Z distribution, standard normal. And we got a negative, but we dropped the negativity like all the rest of the negativity in your life that you need to drop. Just drop it. 1.96 is what we got. And that was our Z star critical value for 95%, right?
Yes.
Easy, right?
Yes.
All right. T star critical values work very similarly. But here's the deal. If I am going to be on a T distribution, is it going to be as tall as this distribution? No. So think about if I take this distribution and I squat it down, what's going to happen to this 95% boundary?
It's going to widen.
It's going to widen, right? So my new distribution, my 95, I'm still capturing 95%. It's just wider because of the shape of it. I've squatted it down so it kind of widens how far 95% goes out. So the T star critical value that's going to cut off that middle 95%, should be outside of what the Z star critical value would have been. Okay? Now, what's the area in this tail right here? It's still 2.5%. I'm just reshaping it. It's not changing percentages, it's just kind of reshaping where everything is. And so this area is the same. So how do I get this? Well, it would seem really stupid to go to inverse norm if I'm not on a normal distribution. However, if you will, please go to inverse or to second vars. Go to second vars in your calculator and prepare to be amazed that there has been something there the whole time. It's never been gone. It's always been there for you. It's like that friend that you don't want around. It never goes away. If you go to second vars and you look right underneath inverse norm, what do you see? Inverse T. Go ahead and go to inverse T. You're going to put in an area of 0.025 because that is still the area of a single tail. But now it wants to know DF. What does DF stand for? Degrees of freedom. And our problem that we are looking at. It says we need the T-star critical value for a 95% confidence interval with a SRS of size n equals 12. If our sample size is 12, what is our degree of freedom? 11. Now, as you guys already said and saw on the picture here, if I squat down the normal curve, it pushes out the 95% area, and I should be outside of the 1.96 that I had before. So I should have a number that's bigger. I go further out to capture that same 95%. Yes?
How did you get area again?
So if I have 95% in the middle, then I have 2.5% on the side here and 2.5% over here. So that's the area of 0.025.
For some reason I thought it'd be like 2.
No, you're good. All right, guys, what did you get? 2.2. Is that further out than the 1.96? Yeah, so this seems about right. Now check this out, you guys. I know this isn't on your paper, and that's totally fine. It's not a big deal. I want you to go through and see something real quick. So go back to second vars, inverse T. Leave your area the same, but for your degrees of freedom, put in 20. So we're just going to up our sample size by only 9. Now, that should not go out as far as the 11 does, okay? You shouldn't have to go as far because I increased my sample size, so I'm going to approach the normal curve. So what did you get when you did degrees of freedom of 20? 2.08. Okay, so look, I'm approaching that Z star already very quickly. Go ahead and do it again. Degrees of freedom this time, do 50. Change your degree of freedom to 50. And what do you get? 2.008. Again, getting closer. Go ahead and do degree of freedom of 100. We're increasing our sample size. We are approaching the normal curve. Our Z-star critical values are becoming or our T-star critical values are getting really close to the Z-star critical value. What do you get for 100?
1.98.
1.98. All right, cool. Last one. Degree of freedom of 250. Degree of freedom 250. What'd you get? 1.97. Notice that I keep approaching the Z-star critical value, but I never pass it, okay? So, and it doesn't take long for it to get there. Make sense? Ish? Cool. All right, I do want to write down, just so you guys have this for reference later, what we did is we did 95% in the middle. We had an area over here of 0.025. And we did inverse T. Inverse T, our area was 0.025. Our degrees of freedom were 11 because n minus 1 is 11 here. And so here is the notation that you can use for what you just found. You found a T star critical value with 11 degrees of freedom and 95% confidence. Kind of a clunky looking notation, but there it is. And what you found that to be was 2.2. If you did a T star critical value for 95% confidence and you got a number of 1.4, I hope that as you continue doing these, you'll realize that you got it wrong. Because if you're doing 95% on a T star critical value, you shouldn't get anything less than the Z star critical value for that same percent. So if you got a 1.4 for 95% confidence, you probably plugged in the wrong area. Okay. All right, let's do one more here. 90% confidence. If we are 90% confident, then what would be the area in a single side? 5%, which is an area of 0.05. We're going to do inverse T. Area is 0.05. Degrees of freedom. All right, it tells us we're doing a 90% confidence interval for a random sample of 48 observations. So what is my degree of freedom?
47.
47. You got it? So we're finding the T star critical value for 47 degrees of freedom and 90% confidence. Again, this should not be anything lower than 1.645. That's the 90% Z star, so it shouldn't be lower than that. It needs to be higher than that. Probably not going to be too much higher because this is a pretty good sample size. 47 is pretty good. What'd you guys get? 1.678. Again, not that far off. Slightly different because our sample size was already pretty good size.
Doesn't matter what we rounded to.
No, it's just sometimes when you've got like these, 8s and 9s at the end, kind of right on the edge. But if you had said no less than 2 decimal places, yeah.
What was the command for it on the calculator?
Second vars,
Okay.
and then it's the third one. I mean the fourth one. Fourth one. Second vars, fourth one.
Thank you.
Yep. All right, you guys. Last thing for today. How to construct the confidence interval and check the conditions. What are the 3 conditions that we check?
Free count. Right now.
Random. Normal. I'm going to put normal at the bottom just because I need more room on that one. And the 10% condition. Okay, cool. How do you guys check the random condition?
SRS.
You just have to say there's an SRS of blah, 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 blah. How do you check the 10% condition? You do math with what formula? Perfect. 10 times the sample size has to be less than the population size. Most of the time we just assume the population's big enough. Okay. Normal. Here's the fun one. We already said we cannot use the large count condition, which consists of n's and p's. We already talked about central limit theorem. Gavin reminded us about the population being approximately normal will work as well. So one of these must be true. Number 1, the population is approximately normal. If that is true, then we say hallelujah and we write down normal, population is normal, and we move on. We have to write nothing else. No math. Nothing other than normal, population is normal. Yay! Okay? In the middle of your test, you can be like, yay! And everyone will know that population was normal. Yay! All right, cool. If this is not true, if you don't read that in the problem, or even worse, you read that the population is skewed, oh no, then your backup plan. N has to be greater than or equal to 30, so the central limit theorem applies. Do both of these have to be true at the same time? No. If the population is normal and it says so in the problem, do you even care what the sample size is? No, not really. I mean, other than you have to use it to plug it in the calculator, but really you don't care. Hey, guys, just a real quick question. If the sample size is 58 and it says that the population was skewed to the right, is that okay? Yeah. Absolutely okay. If the sample size is bigger than 30, my population could be skewed, bi-skewed, modal skewed, I don't care skewed to the up, down, left, right. It don't matter as long as the sample size is bigger than 30. Class, what do we do if our population shape is unknown or we know it's skewed and our sample size is less than 30?
Proceed to caution.
Do we recheck?
Guess what? There's a third option. You're going to love this, guys. You're going to love this. Are you ready? If either of these two things are not true, then you got a third option that you can look at. Here it is. If the sample data is approximately normal. If the sample data is approximately normal. So let's say you have a sample size of 20. You know the population was skewed. You need to see, did my sample turn out normal? Guys, how are you going to know if your sample data is normal? Verify by making a dot plot or box plot. Unit 1. Ensure no strong skewness or outliers. Aren't you guys excited you get to make dot plots and box plots again?
Yes, actually. Well,
All right, now I have a question for you guys. Population is normal. It says it in the problem. Do you have to make a dot plot or a box plot? No. Absolutely not. Population is skewed. The sample size is 32. Do you have to make a box plot or a dot plot? No, absolutely not. Guys, this is a last resort. You will not have to do this on every problem. It's a last resort, okay? All right. Those are the conditions that you'll have to check, and then you can make your confidence interval by using the standard error, which is S sub x over the square root of n. We talked about that a little while ago. That's your standard error. So, standard error of the sample mean, because I'm not using sigma, I'm going to use S sub x. That's called the standard error. And now, the confidence interval formula. Instead of p hat as my point estimate, what would my point estimate be if I'm doing a problem with means? I'll say it again. If I'm doing a problem about means, what would the point estimate be if it's not p hat? But I don't know mu. I'm trying to estimate mu. So what do I use to estimate mu? X bar. Did you just make up a statistic? Did you literally just say mu hat?
I'm sorry.
Wow. All right, X bar plus or minus. Guys, I can't use Z star because I have two levels of variability. So if it's not Z star, what's it going to be? We just learned how to find them. T star. And then the standard error for means, which is what we just wrote down, S sub x over the square root of n. Please remember, x bar is your point estimate. Please remember that when I multiply these two together, the t star critical value and the standard error, I get the margin of error. And then I can take x bar and add the margin of error to get the high estimate and subtract the margin of error to get the low estimate, and that becomes my interval. Do you guys remember yesterday on number 1, part B, you had to make a confidence interval to see if it matched your decision on your hypothesis test? Did you have to do that by hand? Nope, there was a place in the calculator that did it for you, right? Well, this one I will not make you do by hand ever. We will, from the jump, use the calculator on this, okay? All right. All right, guys, great job.